Vivian is an expert on black hole and galaxy evolution, in particular using the most cutting-edge observation techniques like Keck, AO, and also JWST to understand the gas kinematics on black holes and the connections to galaxy evolution. Today she'll be talking about black hole feedback in galaxies. Let's welcome her.
All right, thanks TC. Can you hear me in the back? All right, great. So yeah, thank you for having me back in the Institute giving this colloquium. I realized that the last time I was here is actually nearly a decade ago. So I promise you that some of these slides are actually new because I couldn't have given you a JWST talk back then. And I will also say that here's my group, and maybe half of these kids weren't even born yet 10 years ago. No, that's not true. But probably most of them were not doing astronomy. So I'm going to be telling you a lot about what some of Marina and Justin have been doing, touch upon what Yiqing and Raymond will be doing at the end. But if you're interested in learning about nuclear SEDs of luminous infrared galaxies or distant galaxy mergers from JWST data, please talk to me afterwards. Okay. So I thought that today I will start with the very big picture that probably everyone in this room is familiar with, showing how the galaxies, the universe has evolved since the Big Bang all the way to present day universe. And I always like this perspective of this, cosmology cone, so to speak, because from a very non-biased way that I'm interested in, I think the focus being on the present day galaxies with the Hubble in the nearby universe. But in any case, if you were to sum up, the star formation rate density of these galaxies throughout cosmic time, you might see this famous Mendel plot where the star formation really peaks around redshift 2 or 3, what we call cosmic noon. Of course, JWST may be rewriting the tail end of this distribution on a weekly basis. I haven't checked archive for a week now, but for the most part, between here and cosmic noon, if you really break that down by galaxy population, you would find that beyond a redshift of 0.7 or so, the star formation rate density is dominated by these orange and red points that are the luminous and ultraluminous infrared galaxies. So just what are these galaxies? What are these lurks and ULurks, and why do they appear to govern the star formation history of our past? And so in this galaxy merger scenario, where we have spiral galaxies, gas-rich blue galaxies coming near each other, and then they do this dance, and then they, under the gravitation influence, they start to merge, and that's when the process of feeding gas losing momentum and getting fed into the central supermassive black hole region, and to also trigger nuclear starburst activities. And this is the time when the dust is stored up and reprocesses starlight. And so it's these phases where we're getting the galaxies to appear infrared luminous. And so depending on whom you talk to, of course, the fate of these galaxies may end up being mergers when the AGN's blown out the dust, and then we end up with potentially red ellipticals if there's no new information, new fueling of gas. And so, of course, this whole process of the merger system kind of get placed by theorists on a few giga-years type of time scale, and you can see that it is these particular phases that represent a period of time in the galaxy's lifetime where there's enhanced star formation activity and black hole growth happening. And this is the time when we see that there's a lot of correlation between star formation and AGN activity, so that if we want to understand this starburst-AGN connection, so to speak, do galaxies and black holes actually co-evolve, I choose to study this period of time, this relatively ephemeral, but very important time of a galaxy's lifetime to understand how these processes work in detail. So, of course, we also know from observations that observations of black holes seem to correlate with the properties of the host galaxies, in particular the dispersion of the bulge here at the so-called M-sigma relations. We see that because a lot of these galaxies fall on this M-sigma relation, we think that, okay, well, as the black holes grow, so do their bulges, and vice versa. Of course, there's now a lot of debate about exactly how black holes grow. Like, well, this is particular time points. These are time points where galaxies spend a significant amount of their time, but when they transition, do black holes grow first? Do stars grow, and then the bulge catch up, or vice versa? And so this is kind of giving us a sense of how feeding actually works. And this is how we think that, black holes and the host galaxy, even though they're on such different scales, are related. And of course, at the same time, we've also seen how the lambda CDM predictions of the luminosity functions of galaxies actually overpredict what we observe at both the low luminosity and the high luminosity ends. And we're attributing that to supernovae feedback on this end. And then, of course, on the high luminosity end, it seems that we might need AGN feedback to actually clear out this gas, quench star formation in order to for galaxies and black holes to be on these relations. And so is it really just a chicken and the egg problem, where which one comes first, which one's dominant? But we know now, this is all kind of setting the scene from a decade ago now, that the problem is really not that easy. It's not that simplistic. We know that feedback happens gets manifested in different ways at different scales, in different phases of the gas. And so if you look at it from the gas feedback from a black hole all the way to large galactic scales, it's involved in different phases, the hot plasma phases, warm gas, cold gas, molecular, ionized neutral gas, and then it's obviously comes into, the gas from the galaxy gets fed into the black hole and gets fed back out at these different scales of jets and outflows that I'm going to be talking more about. And so understanding this whole process and how this ecosystem works has become one of the three priority areas that the US National Academy of Science Astrodecadal Survey has prioritized and, for us to do this these few years. So what we want to do is really unveiling this driver of galaxy growth through these different processes, understanding the multiphase gas, understanding how everything changes in a kind of dynamic way. So going back a few years, we've seen these simulations of galaxy mergers and how this multiphase process might work in this what is called the Fire 2 simulations done in this particular paper, where I'm going to show two videos. The left one is the one that's depicting the stellar light, and then the right one is the gas phase, and the different temperatures here represent the gas of different temperatures. And so you can see that as the galaxies are merging, that some of this gas is being blown out at different stages. And you can see an exchange of the different colors of the gas as this process goes on. And so we can actually now quantitatively measure this observationally and to try to compare to simulations. And this particular paper also made actual predictions for how on this temperature density phase space, that how much mass is actually in this warm several thousand 10,000 Kelvin gas, and at different phases. And you can also see that these lines here represent the change in the mass for the different phases as it goes through the merger timeline. And so, these simulations such as this make predictions.
I'm curious, how come the merger random remain this galaxy?
Oh, in this particular case, let's see. Oops, sorry. In this particular case, there's technically no AGN feedback, so that's actually the caveat I was going to come down to next. But this is basically just kind of hydrodynamic simulations of what that process could look like. Yeah. But yeah, so basically it makes predictions for how star formation might be enhanced, how the cool gas content might be altered. And also, what actually happens to this multi-phase gas. And so, like I said a moment ago, the caveat is that this set of simulations actually do not incorporate AGN feedback, and it's tricky, right? To for cosmological simulations, you don't get that zoomed in level, and for these sort of simulations, we're not getting AGN feedback because the physics is complex. So hopefully, we're going to make some breakthrough in this sort of simulation observation comparison, which I'll come back to at the end of the talk. Okay, so. But I'm an observer, so I'm happy that other people are doing the simulation work. And so then I come in from wanting to really help constrain some of these models. And so I work with the goal sample, the Great Observatory All-Sky Lurk Survey. And I have a wonderful set of collaborators, one of whom happens to be in the room here. And so this is the sample where we're looking at about 200 of the local luminous and ultraluminous infrared galaxies, the lurks and U-lurks, where they are mostly represented by major mergers. And so you can see from a glance that these sources all represent, or they span, a range of merging stages, going from like widely separated pairs, all the way to like really messy train wrecks, and then all the way to, I think you can find ARP 220 somewhere, maybe that one, and where they're completely merged. And so you have to have this sort of nice sample in order to statistically sample the different merger stages from the observational point of view to understand the processes that go on. And so we have collected a lot of data for the goal sample across different wavelengths. This is definitely a team effort, and this is a non-exhaustive list of all of the, or some of the publications we've had as a range of, as a function of wavelengths. But I wanted to point this out partially because as of last year, GOES has become not just a multi-wavelength survey, but also a multi-messenger survey, where we're starting to have papers talking about neutrinos. And it turns out U-lurks are actually a good source for neutrinos, and there'll be more coming out of our collaboration with the IceCube team. But for this talk, I'm going to focus mostly on optical and near-infrared observations. So given the complexity of AGN outflows, I've really decided to narrow this talk down into 3 particular questions. How does a gas get transported and powered at different kind of scales? I mentioned that this might get done at differently at the nuclear versus the galactic scales. And how do these outflow actually couple to that multiphase gas in the ISM and influence the host galaxy, and also what role does galaxy interaction really play in this feedback process? So I will demonstrate this through a few case studies before I talk about it as on a survey level. But first of all, to show you some of the pre-JWST era, what did we actually know about feedback based on molecular outflow. And then I'll show you some early JWST results from a couple years ago that talks about inflows and outflows and shocks. And then lastly, some of the work that my postdoc's been working on and stringing kind of all of these together. Okay, so let's get started. Here is one of my favorite U-lurk. This is McCarran 273. It looks like a toothbrush. And then when we talk about like nuclear scales, I'm really talking about like this tiny part. And so we had a lot of Keck adaptive optics OSIRIS data that shows, before the JWST NIRSPEC age of how the molecular gas and ionized gas looks like in the center of these galaxies. So with very fine plate scale, we're looking at, this is iron 2 in H band, and you can really see how well the gas is rotating about this this nucleus here. And this is a system that I picked out because it's a really interesting, like I said, a personal favorite of mine. There is an X-ray AGN here in case you're wondering why this point is so bright. But there's actually very ambiguous information about like what might be powering the source of this northern region. There might be supernovae, might be supernovae remnants, or nuclear star clusters. And so based on our work, what we found is that projecting the IFU data I just saw, this is iron 2 flux map, we actually see a very bright point in the southeast nucleus, which I'll come back to in a slide or so, that there's this diffuse emission going on in this northern nucleus. And because we have really high spatial resolution, basically we're talking about like 0.05 arc seconds full width half max, and I think at this distance, this comes out to about 30 parsecs per pixel. We see this rotation in the velocity field that actually allows us to characterize the Keplerian motion of the disk around this particular region. And so what we found by modeling this gas that's actually result within the black hole sphere influence, we found a black hole, or sorry, a source that is 1 billion solar masses in the center of this region. And this actually matches really well with a measurement from a mega maser, which is kind of taken as a golden standard for mass determinations for black holes if they're detected. And so it gives us pretty good confidence that there is a very compact object of 1 billion solar masses in here, which by our various arguments that we think this is a black hole which may not necessarily, which would be super obscured. And it was, and so with knowing that, we then followed up with deep Chandra data, 200 kiloseconds, and we actually were able to detect 2 X-ray sources in this particular region, so to verify the dual AGN nature in this source. And so this is the type of technique that allows us to kind of do dynamical black hole masses, and we also have other works that have expanded on that. But for this particular talk, I want to focus on the gas kinematics. And so when we looked at the molecular hydrogen lines, also in the near infrared, this is actually a little bit coarser resolution. Now, this is 0.1 arc second, so it's the same thing as JWST near spec. It's our coarsest resolution sampled by Keck Osiris. And what we see, again, here's a flux map of molecular hydrogen, the velocity map, very similar to the iron 2 that I just showed. And here's the molecular hydrogen's velocity dispersion map. And you can kind of see this cone shape, which we're taking basically as the telltale sign of a nuclear outflow coming out of that rotating disk. And within this picture, we then were able to calculate, what the outflow rates were, the molecular mass that were outflowing was, and energetics, et cetera. And so these are the numbers that we really need or want to compare to the fire simulations at similar parsecs, similar spatial resolutions. And so this is, of course, one really interesting object. We had a sample of about 30-some galaxy system where we targeted 50 nuclei over the course of many Keck nights at similar resolutions. And so together with my colleague Anne Metling from the University of Toledo, we have looked into a lot of different science cases, molecular outflows, dual AGN, nuclear disk, black hole masses, et cetera. And so this is the type of data quality that we were able to have, and it really facilitated our comparisons with later JWST near spec observations. And so in particular, what I was really interested in is to understand this nuclear feedback, nuclear outflow, and how it might affect the star formation inside this small region. And so if we looked at this is now the dust-corrected star formation rate as a function of here merger class. So kind of from widely separated merging pairs to like coalesced pairs. We kind of see this tentative positive correlation with the star formation rate, and also vice versa with the separation between the pairs. So as you get closer and closer, it seems that star formation rate does indeed increase. And so is this, a case that we're seeing signs of positive feedback happening at the scales of, tens of parsecs resolution inside the nuclei of these lurks and ULurks. And we found that also when we look at the molecular hydrogen normalized by the bracket gamma, normalized by hydrogen recombination line, we see that actually there seems to be a lot of shocked molecular hydrogen that are prevalent around galaxies that are hosting AGN, But when we actually try to correlate that with the strength of the AGN through the mid-infrared or the bolometric AGN fraction, we don't really see any clear trends. And so we were a little bit puzzled by that. And so we thought, okay, maybe in the near-infrared, great, we're getting through some of the dust, but it's not enough. So we used that as a basis for trying to get JWST mid-infrared data to really understand what might be going on in the center to see past more of the dust. And so from that paper, we selected a sample of 7 sources that have these more promising signs of nuclear outflows. And so this is an outflow selected sample where we're trying to figure out, what's going on with the geometry of the inner AGN region. Is it dusty? Is it and how much like metal might be around there? And so this is all kind of getting down to the question of how do supermassive black holes grow in mergers, and we figuring out that this is an obscure phase where AGNs might be embedded fully in the dust before they really blow out in a cocoon. So this allows us to, what this leads into, our JWST campaign of the GOALS survey, where we're trying to investigate the starburst AGN connections in these galaxy mergers. In particular, with the early release science program, we targeted the nuclei of the 4 sources that were selected from the GOALS sample. Now, these were selected to have a range of silicate absorptions and the mid-infrared properties, and I mentioned the nuclei, but that's only the MIRI, the IFU field of view. We do have imaging for the entire source as well. I think I showed the JWST image of the Vivian 114 as a whole in my title slide. And just on these data sets so far, we have a number of published papers and a few more on the horizon. And so these may be outdated numbers as well, given. But the idea is that we started off with these source 4 galaxies, and we've learned, as you'll see, quite a number of interesting new insights. But since then, we also have gotten more JWST data on the GOALS sample. So in cycle 1, our sample of the 7 nuclear outflow candidates was awarded. We also have another program that targeting compact obscure nuclei was selected as well. And in cycle 2, our ULERC program was also selected. So altogether, we have probably on the order of like 2 dozens or so LERCs and ULERCs in our GOALS samples that now have JWST data in some way. So it's getting to be a very exciting data set that we can start to do some statistical constraints. So let me now jump to what we've learned in the last couple years from our early JWST results. So here I've picked this one of the 4 ERS targets, NGC 7469. I picked it because this is the one source in our ERS sample of 4 galaxies that has a clear AGN nucleus. It's a Seifert 1.5 nucleus, and it's completely phase on. So there's a AGN in here surrounded by a star-forming ring. As you can see, this is the HST image. The JWST in this particular case, it may not look like there's too dramatic of differences, but what we're really seeing is that one of our imaging bands is the 7.7 micron, showing a lot of the PA bands that's actually tracing the stars in our spiral arms here. So this is okay, so this is the MIRI data. So the MIRI data goes from 5 to 28 microns or so, and of course it's an IFU. It's my favorite instrument aboard JWST, and we can see that here are 3 lines that I've particularly picked out in channel 1, which goes from about 5 to 7-ish, 8 micron. Don't quote me on that part. But this is the iron 2 line, molecular hydrogen, and argon 2. And so you can see that the low ionization lines, these 2, look very different from a molecular gas. And you can see the star-forming ring is well depicted in the low ionization gas, but then the molecular gas actually resembles that from of the cold gas from ALMA a little bit more, and you can see some of the little spiral arms feeding in. And so, but overall, their velocity look kind of interesting, but similar. But I'm going to come back to this little enhanced region of molecular hydrogen and also of iron in just a little bit. And so this is the type of data that we're getting, that a lot of the cooler gas and what we have been able to probe previously with just Keck OSIRIS. And so here, really interesting again, is showing the channel 1 spectrum from 5 to 7.5 micron. And this now I've dissected this central nuclear region into a grid. And so you can see that this is the nuclear spectrum from that, and then the other ones are depicting the regions from around the nucleus. And I highlight in particular this magnesium 5 line. This is a line that's considered one of the high ionization line. The ionization potential is, I think, 130 some eV. So the fact that we see these lines, it is that most likely it is ionized by the AGN ionization. And so, and you can see in this line that there's a really obvious blue shift in these lines. And so coronal lines are also really good at actually picking out these non-rotational outflows. And so this is what we see in this galaxy, particularly extending to the eastern region. And when we look at all of the line profiles for the high ionization species as well as the low ionization species and the molecular lines in NGC 7469 in the nucleus, you see this blue asymmetric wing in all of the high ionization species, but not so much in the low ionization species, nor the molecular lines. And so, doing some calculations from these lines and measuring the full width half max as a function of ionization potential, we see that there's actually a decelerating stratified AGN-driven outflow in this galaxy, and we're able to quantify the mass outflow rate and as well as the black hole accretion rate in this source using some scaling relations. And so what we're able to get from this data set is that inside the nucleus, even though and there's a face-on galaxy, we can see there's outflows that's kind of blowing towards us, as well as shocks that is delivering into the ISM in the galaxy, all inside this rotating star forming ring. And so this is consistent with some of the large-scale IFU data that other people have seen in the optical, but now we get a very clear picture of what might be driving it directly from the center source. And so I've presented so far the MIRI data of this source. MIRI is wonderful. It works in the mid-infrared, shows us the cooler gas, but with the near-infrared, we can actually sample warmer gas, and also in some of the more familiar lines to most of us. So here is actually near-spec data that my postdoc Marina has been working on and that she followed up with. And so you can see that we have the G140, G235, G395 spectra, again, very rich in features, and this is actually much more sensitive than the Keck OSIRIS data that I've shown before. So in this particular case, Marina looked at the Passion alpha velocities and found that, well, actually it looks similar to what we showed before with the MIRI data, but actually if we take out the rotational component, we might be seeing some of the residuals that looks like that might resemble signatures of an inflow. And so if we assume that this is in fact inflowing gas going into the center, we were able to calculate a mass inflow rate to compare with the supermassive black hole accretion rate that I showed before, and turns out that there's probably a lot more mass going into the black hole that we're assuming that it's that the supermassive black hole is accreting. So this means that we're going to see a lot of gas build up in the central kiloparsec region on the timescales of these mergers that we're talking about. And so this is really interesting because if you want to understand feeding of supermassive black holes and what time scales, we need to see that the properties or the amount of gas that's coming in and it being accreted onto black holes kind of at the level that we've calculated here. So Marina went on and kind of looked at the lying ratio. So these are just lying ratio of iron 2 over Paschen beta and H2 over bracket gamma. So similar to optical PPT diagrams, but now in the near infrared. And we can see that there's a lot of the star forming ring is actually being picked out now. I should say that these are empirically determined lines, so they're not perfect, not like as well studied as the optical PPT lines, but you can still see that the star forming ring is shown in this sort of line ratios, and we see a lot of high excitation lines either from AGN or maybe even shocks in that small region where we saw high dispersion in molecular hydrogen in the MIRI data. So this is actually kind of interesting because we found that this is co-located with a compact radio jet core structure. And so how radio jets might be shocking the gas, it seems to be something that we are now picking up as well in these sources. Another thing that we can study with the JWST data is looking at these the dust grains with the PA lines, the PAH lines. And so here's some work led by Thomas Lai, and he showed here's the PA 6.2 maps that shows some of the clumpiness of the star forming ring in 7469 really well. And if you were to look at how the 6.2 to 7.7 ratio changes as a function of neon 3 to neon 2, so you can see that basically there are larger grains closer in as you get closer in towards a harder radiation field, which could be a sign that the smaller grains might be destroyed by the AGN hardness as you get closer to the region. Lastly, on this galaxy, with the imaging data, Thomas Bond from Hiroshima was able to kind of calculate and find these embedded young stellar populations, which were not seen before in HST data. And so by looking at and picking up these additional star clusters that previously were obscured by dust, we actually found that there are a lot more younger stars in the center of these regions, and they're pretty young, and so we can actually we're finding a lot more, like 3 times as many of the young stars that were previously embedded. And so and there's a lot more that our team has done, with the early release science data. But I want to now kind of switch topics to coming back to this multi-scale, multi-phase feedback that I promised you from the start. And so this galaxy is VV340. Now this is a laundry list of properties that, unless you care about VV340, you probably don't need to read through. Just know that this is a moderate luminosity LIRC. So for all intents and purposes, it's kind of like a normal galaxy merger for whatever normal means. There's an edge-on component and a phase-on component here. They're relatively well separated, and then the molecular mass and the star formation rate. Those are all kind of puts it at a very relatively normal LIRC for all intents and purposes. And so what we have, again, is the JWST MIRI data. This is one of our targets that was selected in our nucleus outflow sample. And so we have JWST MIRI data of showing the center part, but also we've put together mosaic enough Keck KCWA data, so we get wide field IFU data mosaic out to like 24 kiloparsecs or so, much coarser sampling, but now we can study how the gas from the inside may or may not be traveling to the outskirts of the galaxy. And so this is work led by my postdoc Justin Cater, and what he's shown here is a lot of these lines from the JWST data set from molecular gas, but all these ionized gas from low ionization potential all the way to high ionization potential. So anything above here is sort of like this coronal gas that's mostly excited by AGN. And it's really interesting. You can see that the gas, because this is an etch-on disk, this is the northern component, a lot of the low ionization and molecular gas is actually on the disk itself. But at some point, you start seeing this extraplanar gas that is coming out of the central AGN. And so we're actually seeing, so I'll just focus on maybe the neon 5 line, which is a favorite coronal lines that AGN people like to study. And it looks extremely collimated and has a really interesting structure. So if I were to overlay this on the HST image, what you can see is that the neon 5 gas is extending about 6 kiloparsecs. This is one of the largest and most coherent collimated coronal line structures that's been seen in the galaxy. And I think this is partially because we're in a very favorable orientation where you get this edge-on galaxy, so we can actually see that even though this is projected distance, this is actually quite large. And so here I'm showing the channel maps, kind of going from the blue to the red here, from so the blue minus 400 kilometers per second all the way to minus 150. This is at 0, and then going to the red all the way to 400 seconds. And so you can see, really interestingly, not just that the gas is coming off of the plane, but you can kind of see this little forky structure as well, if you look closely. At least our referee did, and we did as well. And so what's really going on? And Justin calculated, some of the mass outflow rates and energetics. But what we want to know is this actually gas that will eventually get out of the galaxy and get to quench the galaxy? So in our Keck KCW data, where I showed we have a larger mosaic data, now I'm showing the O3 line, which is a low ionization line, but usually people use it to study outflows. And you can see that it's basically completely aligned with the mid-infrared neon 5 emission that we had seen. And so we've done PPT diagnostics to reveal that this excitation is really likely due to AGN photoionization. But those are just two pieces of the puzzles. We also found archival radial data on this galaxy that shows not just radio emission, but an S-shaped radio jet that is aligned with the emissions that we've seen. So here I'm overplotting in white contours the 6 gigahertz radio jets, and you can see this like S-shaped, and that is also very extended. The straightened part, collimated part, is completely aligned with the neon 5 from JWST, and then the S-shaped here might actually indicate jet precession. And we found a paper that kind of simulates jet precession, and we're like, well, it looks completely like it. And so we think that what's happening is that there's actually a precessing radio jet in this galaxy that might be driving some of the outflows. And so Justin went ahead and actually modeled the radio data with ballistic models of the helical precessing jet. So here I'm showing the radio data, and that gets carried through to the contours. And here the underlying image is actually the model of that precessing radio jet, and then carried out to these green plots are the what's called the trace of where that jet might have been if it was precessing for some time. And we've found a precession angle or precessing period of like 800,000 years. And all of this actually seems to match, the large scale O3 lines that we had seen before. And so this is just a 3D depiction of that. So we're really excited by what we found here, but of course we wanted to be sure this is what might be driving it. So the kinematics, we do a deeper PV diagrams of those emission lines. So here is that the neon 5 line, and then that's the O3 line. And so when we try to compare the kinematics of what the kinematics of the gas would have looked like if from just pure rotation on the disk versus from outflows, we found that actually they match pretty well to the outflow model. So so this was actually one results that Justin has been working really hard on, and I'm happy to say that like as of a few weeks ago, like our referees, all 4 of the referees were very happy with our corrections. So hopefully the paper will come out in the next few months in Science. And so what this one case studies has kind of told us about how aging outflows might work is that, well, precession may provide one mechanism for collimated jets, and then that can in turn drive outflows. But this outflow, even though it might not be actually removing all of the star-forming gas completely, it can at least accelerate depletion timescale via heating up of the gas and depositing shocks. Now, I'm not going to attempt to answer how galaxy interaction plays a role in this from one galaxy, but this is where we have we have a sample now to answer this question more statistically. So we now have put together probably somewhere on the order of 20 to 30 objects with this merging sequence with IFS data, both from the JWST side and from the Keck side, to really scale, probe this multi-scale gas in a very complementary way, and to see how outflows play a role in driving the galaxy evolution. So here is the survey, molecular gas survey that Marina has been working on. And so she started off with the 7 galaxies in the Cycle 1 program, but she'll be expanding this to the entire sample with GOL's JWST data. And so we're seeing already that even inside the central region, we have a variety of H2 line profiles. So the molecular gas could be doing really weird and interesting things. And so if you were to look at what the 2D maps look like for this galaxy, so here is 7469, which I already talked about, the molecular gas being kind of inflowing from the spiral arms when displaying shocks in the dispersion map, but also Macarian 273, which, if you recall from earlier in my talk, I showed the Keck Osiris data. Now we have JWST data showing much more deeper data of the molecular hydrogen line, and this actually looks very interesting because it starts to show these forks that we saw in VV340 that we didn't see before in Keck Osiris data, and also some enhanced dispersion and very blue shifted gas. But also I want to highlight one other source from this sample. So IRS 01364, this is something that ESO fellow Yi-Ching Song has been working on. It's a relatively further away galaxy merger, but if you look at this dispersion map of the H2, this is like a gas that's very cone-like, and from a galaxy that we had not detected AGN before. And so she's seeing a high ionization line in that galaxy for the first time, and also really interesting gas kinematics. So hopefully stay tuned for that paper to be coming. And then from the low ionization Keck side, Justin is now finalizing all of the data that we've taken over the past few years of all the Keck data. So we also have about 20, 30 objects where we have observed with Keck KCWI, KCRM, here overlaid on the HST images. The green is the O3 emission, so you can see that there's a variety. Some of them are this is actually might not be received from the scaling, but this is 01364. The object that Yi-Ching's working on, it kind of goes out pretty far from the galaxy, and then R220, you have these crazy loops, and VV340, of course. And so with this data set, not only is Justin doing kind of the basic PPT diagrams, but we're also actually looking at the neutral gas. We have coverage of the sodium 1D line, and to try to understand, how the energetics and energy is deposited in ISM, and hopefully maybe looking at metallicities as well. So to kind of wrap up a little bit, this is actually what our research group has been focusing on, trying to understand this multi-phase analysis of this gas and nearby lurks and ULurks, a lot of which I've shown you. trying to understand, not just the ionized phase, but also the multiphase gas and how the comparison to the simulations may go. But we also have a control sample of not mergers, but nearby AGNs with Seiferts with reversion mapped AGN black hole masses. So my student Raymond has been working on kind of a pilot sample, but we'll soon be looking at the entire sample of 30 galaxies as a control to what, if not merger dynamics, could be causing all of this activities. And in this particular paper, he's focusing on like the difference of gas kinematics between, difference in kinematics between the gas and the stars, and where things place on M-sigma relations. But we'll be expanding that to the larger sample. And so I wanted to just quickly mention a little bit off topic, but I am starting a new kind of project, kind of expanding into the far infrared, something I'm completely, new to, but it's been really interesting. I don't know if any of you are familiar with kind of the the recent NASA APEX competition that's been going on, for X-ray versus far infrared probes that hopefully we'll be sending into space soon. This is actually mission agnostic. We don't particularly endorse any particular far infrared missions, but we think that hopefully there will be a far infrared mission in the future. And so if that were the case, we need to be prepared and do precursor science that would allow us to understand the far infrared source confusion. And so the idea here is to then try to do some simulations to understand the extragalactic source confusion, attach far infrared fine structure line properties to them to understand star formation and black holes. And part of it is to guide the architecture of future far infrared missions, so we know like what kind of sensitivity we're going to get for whatever mirrors that the budget would allow us to build. So that brings me to my final slide. And so hopefully I've convinced you that multi-phase inflows, outflows, feedback, they're really interesting and important for us to understand in detail using high resolution IFU data. If we want to see how these processes manifest themselves in particularly galaxy mergers, where there's a lot of processes that involve both AGN activities and star formation activities. As I mentioned, I really am doing a lot of mid-infrared IFU data, but IFU spectroscopy analyses. But our team has also been using mid-infrared data to understand embedded nature of these nuclear cores, and also things are a little bit interesting right now. We don't understand everything that we've seen so far, but hopefully next time I come back, I'll give you fuller answers to all that. And so I do have an open postdoc ad out now, and that is going to be person will hopefully be helping us to understand some of the NSF and NASA projects that I will be doing very soon. So I guess I'll leave it there and take questions. Thank you.
Very cool plot on the O3 distribution compared to radio. I was wondering specifically on that, the length and size of the radio emission, neon 5 emission, oxygen 3, but maybe specifically oxygen 3 radio. I'm sorry, yeah.
Sorry, next one.
It's a lot of information, yes.
Yeah.
I was wondering, the lengths are very different between radio emission compared to oxygen 3.
Mm-hmm.
And my limited knowledge specifically on this is that usually the radio jet would be the much longer, larger one. Does this suggest that we are missing a lot of radio feedback in radio sample surveys that they can actually appear as compact sources even at higher redshift? And can you comment on, maybe I'm sorry, it's a long question, because a lot of the simulations that's using AGN feedback always assume just a very strong radio emission, yet this source is clearly a highly radiative source. Does this also mean that we're over our prescription of AGN feedback in simulation may be not always appropriate anymore given this new observational data?
Okay, so I'm gonna preface my answer by saying that I'm not about to invalidate a whole field of radio jets from one source, but I will say that this source, it was really interesting to us, partially because it was actually a radio quiet source, right? And it doesn't, at least as far as we can tell, there's no like large radio lobes and things. So, and also this is archival radio data that I think that maybe different PIs has taken data at different configurations that were not somehow put together, and so we only saw this for the first time with a radio jet. So what I will say is that let me answer maybe the first part of the question, why they seem to be at different scales. So if you buy the scenario that I'm proposing, which is that the radio jet itself is doing the precession dance, this is the the trajectory that it's, I'll go back to this one. So this is probably what's happened in the past. So what we're catching it is the current cycle. Yeah. But then the gas that were driven out was already on the previous cycle. So that's why the low O3 gas is a lot more extended along the past trajectories that this this radio jet has been doing. If you think about this not as like a 2D projection, but a 3D thing, so what it would be doing is the silly dance I'm waving around with my arms with, but what it actually does is it can push out gas in the past. Now the question is, why do we only see one cycle? But like I said, it's archival data, so we didn't get to choose the depth of the radio emission. I don't know that if we get like maybe radio observations at different frequencies, or maybe that we will be able to see the larger scale a little better. What we think is that, at least in this particular case, radio jet seems to be able to drive gas to large scales. Now, you also pointed out that the radio jet actually, the radio jet really only kind of overlaps with like this part of the neon 5 gas. I showed the field of view of Miri here in particular because I know it doesn't show very well in this particular plot, but I think it keeps going. Yeah, this sensitivity drop off is not because of the gas, it's just the field of view of the way that the Miri works. So it would be nice if we have more data, JWST data, to say, hey, was the neon 5 gas also follows the trajectory of the O3 or radio jet? But without more data, I can't tell. I wish somebody put in a JWST proposal for that. But,
Thank you.
yeah.
More questions for you? I have a question about the inflow of gas. There's a mass estimated for feeding because of once you subtract out the normal rotation, you interpret that as a sign of feeding of the gas. I mean, exactly how that works. I mean, there's a residual, but how exactly do you interpret that spiral arm that you draw as a feeding of gas instead of something else? Maybe the rotation of another structure.
I mean, yes, that's entirely plausible. So the inflow, it's our favorite scenario. And if we assume that, well, so I think that, yes, I stand by what I said, but also in this particular case, we had the molecular gas map that showed us, sorry, I had to keep going in the wrong direction. The molecular gas map that actually also show, these spiral arms, that it's actually the same as what we see in CO gas from ALMA. And so kind of a little bit of a multiple lines of evidence thing that have us think that, the inflow scenario is probably more likely than other explanations, but yeah.
Speaking of molecular gas, I mean, for the other source where you have these nice radio jets and ionized gas outflows, I mean, do you have molecular gas data on that, and do you see also molecular outflows for this particular source? And if you do, what are the mass loading factors, different traces of gas?
Very good question. The short answer is no. So we had some ALMA data, and we also looked at the H2 with, well, I guess I showed the H2 previously. The H2 seems to be mostly on the disk. We don't see much of it off the disk in the outflow. And so, and the same as what we looked when we checked out ALMA CO data, it's that, it seems to be on the disk, but not really so much off. And so we were puzzled by that too, we and the referees. And so what we think by... I was gonna say, are you the good referee? No, I'm just kidding. Yeah, so it was really puzzling. We think that maybe because the molecular gas would be a lot heavier and you need like maybe somehow either you don't have enough energy to push out the molecular gas, or somehow it's not being pushed out that way, or maybe this has actually been dissociated. And I don't remember if we had an argument for one versus the other at this point, but the short answer to your question is no, we actually don't see molecular in the outflows beyond at this scale. Now that said, I think there was some hints. I mean, the fact that it fell into this selection in the first place was that we saw some level of H2 enhancement in our Keck Osiris data, and I think that's a much smaller scale. So is it that either, like I said, it's still consistent with either the scenario that is trying to push but doesn't have enough energy to push it that far out, or that it gets dissociated because, I don't know the answer to that. But it will be really interesting if we can get deeper ALMA data. That would be,
or samples.
Or yeah. Exactly.
Yeah, so follow up on the multiphase outflow. So yeah, you mentioned the sodium 1D absorption. So yeah, maybe it's not still there, but could you comment more? For example, that distribution trace either, well, there's no molecular, but does that say trace the ionized outflow or whatever? You can comment.
Yeah, so I do not have a backup slide for that, but maybe I can show you things offline on my computer. So what I recall is that Justin was able to see neutral gas. Well, first of all, because it's in sodium 1D absorption, we expect it to be mostly on top of the galaxy where we have starlight lighting it from the back. However, we actually saw some what we think could be sodium 1D emission that is just off of the galaxy for a few of these sources. I don't have a slide for it because we're still trying to figure out if that's true or not. I don't want to spread false information, but we're really excited that we might be seeing like neutral gas in emission that's just outside of the galaxy, like and along with some of these outflows. So once we do a deeper dive into that, I will have hopefully more exciting answer for you. Yeah.
I was wondering if you observed, at these scales of the orders of tens of parsecs, you observe the Keplerian rotation in the objects in the central regions. And I was wondering at these scales, I expect that inflowing motion should be important, and you show us at least one galaxy in which you observe like some kind of inflowing motion. From the kinematic perspective, trying to model inflows or outflows or barrel flows is quite challenging because it's difficult to associate like a non-circular rotation to an inflow, outflow, or barrel-like flow or spiral. But I was just curious that at these scales, I think that it would be really interesting to see the contribution of inflowing motions at very small scale. We expect that the gas falls into the center of the galaxy in the nuclear region. And this might also induce, for instance, these outflows that we are observing, for instance, in this particular object. It was more than a comment.
Yes. I mean, for inflows, it's not something that we were looking for in particular. We knew, like for the survey paper that Marina is working on, it's mostly with MIRI data, and MIRI data, we're looking at more like 0.2, 0.3 arc seconds resolution, which at these rest shifts, it's more like 0.3. That's, I don't know, hundreds of parsec maybe on the order. So it's a larger, and so the one that I showed with the inflow, that one was with near spec data from the ERS program, and that one we had 0.1 arc seconds resolution. So the short answer is that we haven't looked because inflow wasn't one of the science goals, but so right now we wanted to look at least for the molecular gases and the nuclear scales, you know, how much mass is in the outflow versus how much mass is, you know, in total, what are temperatures of the gas with all the H2 lines that we have. But, you know, if we try to look for inflows, and then maybe we can, that's something that we can see if we can say anything interesting about. I suspect though that with the merger samples that we have seen nuclear disks around all of these, but, you know, whether or not we'll be able to see inflows probably depends a little bit on the geometry of the systems and maybe obscurity. But yeah, like I said, we've had to look closer for that.
Okay, can you use it for topic lines?
Sorry?
Can you use it on the system on the outgoing on the atomic? Atomic lines.
Atomic lines.
Atomic.
Isotopic lines.
Yeah, because they will be quite different from. The ratio will be very different from the normal stars and star.
Yeah, I think that would be interesting. We're starting to explore beyond just the lines that like we're showing in this paper. So I haven't looked into that, but I mean that's something that we should definitely explore and see if we can find out more about the densities and of the gas. So is that what you're trying to get at? To maybe using those lines.
I'm just trying to get the I have to result because there are a lot of supernova going. So you'll be able to have tools to see supernova. Be great.
Yeah. I mean, that would be cool. Yeah, for sure. I would probably have to talk to some friends to help us with that. But yeah, I think that would be interesting to explore. Yeah, thank you.
Can I ask one more? Sure. I'm more interested on the black hole aspect, but one big question I guess we have is about the final parsec problem, where you need to transport gas from like the whole galaxy into the centroid, and that seems to be a very difficult thing to do. But given the fact that now we have a relatively, I think, good sample of typical AGNs, inflow rate, outflow rates, can we start to talk about the availability of molecular gas or material to fuel AGN phase at this point? Perhaps we don't need the gas from outskirts, or just the molecular gas inside the 1 kiloparsec is enough. Can we say anything about that now or soon?
So at least for our merger samples, we're not at the scales for sure to probe that into that region. I mean, this is a topic that's near and dear to my heart, so I would like to be able to do that with larger mirrors at some point. But I would say that based on when we first looked at the gas and we were able to find these like nuclear gas disks in our galaxy mergers, we were able to determine for sample, the dynamical black hole mass. And I put that in quotes because even though we're resolving within the sphere of influence of the black holes, we think that we're still basically, what we're calculating is ultimately enclosed mass, right? Enclosed mass within tens of parsecs. So I want to be a little bit conservative. And if we are able to find consistently more of these like inflows and calculated inflow rates, then we can actually say more about how much gas might be being piled up within like the regions of interest that you said. And so in that case, even if we don't, I think it will take, the next level of facilities for us to actually see the kinematics of the gas at that level, but at least we can start saying, like, is there even gas to begin with for us to accrete? So yeah. So in that sense, in letter sense, and yes, we're doing that now, right now. But if to really do like detailed modeling, we probably need better IMUs. Yeah.
Okay. Since we're in the session, I mean, we're gonna have coffee and snacks outside. So if you have more questions, we'll come stay on, talk to Vivian. And let's thank Vivian again.